Good morning. I am Haijun Su, professor in the Intelligent Design and Robotics Laboratory in the Department of Mechanical and Aerospace Engineering at The Ohio State University. This talk asks a deliberately narrow question: where are current large language models on the path toward genuinely capable kinematics reasoning? We benchmark them on classical problems and on the demanding general six-revolute inverse kinematics challenge. First, a timing caveat. This study captures late 2025 and early 2026. Today's coding agents pair a model with a harness, a workspace, tools, shell access, tests, and iteration. Skills, harness engineering, loop engineering, and graph engineering make execution stronger. But stronger execution is not the same as discovering a new kinematic derivation. Our goal is not to ask whether a chatbot can explain inverse kinematics. We assess whether an LLM can help produce executable, validated solver pipelines for hard kinematics problems. The central distinction is between plausible mathematical prose and solver code that survives independent checks. We frame this as a domain-specific AGI benchmark. Imagine that post-1980 solutions were unavailable in the training data. Could an AI reconstruct a solution root from the underlying mechanics and algebra? The answer depends on the problem family, the available evidence, and how much expert method selection is supplied. The five-level hierarchy makes that distinction visible. At the lower levels, an agent can reproduce classroom analyses or solve well-specified exercises. Higher levels demand guided research, then autonomous discovery. Our evidence will support strong level 3 performance on documented procedures, while level 4 and level 5 remain much more demanding claims. The benchmark suite spans planar and spherical linkages, spatial SS dyad synthesis, Stewart-Goff forward kinematics, and general six-revolute inverse kinematics. Difficulty is not just polynomial degree. It grows when symbolic bookkeeping, numerical stability, or the choice of elimination strategy becomes decisive. The workflow is human-AI collaboration. The expert supplies the source materials, constraints, candidate strategy, and validation criteria. The agent writes and runs the code. The final result is accepted only after the requested evidence is produced. This matters because a final single-shot success can hide many earlier corrective loops. Now to the central challenge, General 6R inverse kinematics. Given a desired end effector pose, recover every joint configuration that realizes it. For a general geometry, this is a coupled nonlinear system, and we need not merely one local numerical answer, but all physically relevant assembly configurations. Why use this problem? A general six-revolute manipulator can have as many as 16 real solutions, and its equations combine trigonometry, geometry, and numerical conditioning. It is therefore a useful test of whether the agent can follow a non-trivial symbolic route, rather than just call a generic nonlinear solver. The successful route begins with a kinematic split at joint 3. Rearranging the forward kinematics isolates two subchains and exposes a structured relation between them. This is a mathematical design choice. The model can implement it, but the choice of this decomposition is part of the expert contribution. That split produces 14 bilinear constraints. Their shared linear structure is more important than any individual equation. It gives us a route toward null spaces, half-angle substitutions, and polynomial elimination instead of an uncontrolled expansion of the original trigonometric system. This is the solver pipeline. We start from forward kinematics, form the 14 constraints, use a left null space, apply half-angle variables, eliminate selected unknowns, and recover candidate joint angles. The value of the pipeline is that every stage produces an intermediate object that can be inspected and tested. The model did not begin with the correct pipeline. Early failures came from equation extraction errors, unstable numerical steps, and incomplete validation. These are not cosmetic issues. Any one of them can produce an apparently reasonable answer that misses valid configurations or reports false ones. For validation, we use the Mensur-Doherty benchmark, a known 16-root case. A credible solver must recover the full solution set and satisfy forward kinematics residual checks. This is why benchmarks with known root counts are valuable. They make omission and duplication visible. After refinement, the solver recovers all 16 solutions with small residuals. The point is not just the headline number. Each recovered root is checked through the original forward kinematics, so success is tied to a physical pose rather than to a polynomial manipulation alone. The implementation is also practical. The reported Python and C++ timings show that the symbolic derivation can be converted into a usable numerical solver. Still, runtime is a secondary result here. The primary contribution is the validated route from a difficult derivation to executable code. The special 6R architecture with parallel joins provides a useful boundary case. Its geometry changes the algebraic structure and permits additional decoupling. The agent can exploit that structure when it is stated clearly, which is closer to guided research intelligence than to fully autonomous discovery. The Stewart-Goff companion case makes the contrast sharper. Given 6 late lengths, recover all platform poses. A documented exact arithmetic elimination sequence leads to a degree 40 polynomial. Here, the agent succeeded when it faithfully translated a published sequence and preserved the required validation checks. Paper 2 broadens this exercise beyond robot inverse kinematics. It covers linkage problems, spatial SS dyads, and Stewart-Goff forward kinematics, then turns the lessons into a practical guide for setting up an evidence-producing agentic workspace. So what intelligence level do the results support? Strong level 3, guided research intelligence on documented complex pipelines with expert-specified routes and independent validation. We do not claim autonomous invention of a new solver architecture. The method selector remains the critical human role. The limitations follow directly. These are classical reproducible benchmarks rather than open-ended discovery problems. Results depend on prompt specificity, tool access, and validation design. A reliable code generation loop should therefore be interpreted as an engineering capability, not as proof of unrestricted mathematical autonomy. The practical takeaway is reproducibility. Prompts, generated code, and benchmark reports are available through the listed repositories. A reusable agent skill can package the problem. Family method, tools, and checks, it is reproducible, but it still encodes the expertise that was supplied during the study. Thank you. The main message is simple. Current agents can compress difficult implementation work when the kinematic route and acceptance tests are explicit. I welcome questions, and the appendix contains the detailed benchmark tables and prompt structure.